All right, guys, so this is our intro to Unit 4. The major theme for this chapter is congruent triangles. That's going to be the main idea. Before we get to congruent triangles, though, we got to talk about triangles and all the vocabulary that goes with them. But also, we need to talk about what congruent means in those shapes. Of course, there'll be other things that we do throughout the unit, but the main idea is congruent triangles. How do we know when triangles are congruent? We'll be talking about that a different day. For right now, though, we're going to be talking about triangles in general. So let's start with how do we name triangles? We have 3 ways to name triangles by their sides. The first one is scalene, and a scalene triangle means that they have no equal sides, or no sides are equal. So how could we draw that out? Well, if I have a triangle here and I wanted to show someone, hey, this is scalene, I could use different tick marks here, right? If I saw that, I'd call that a scalene triangle. Or I could put just numbers on there, right? If I call this like 5, call this like 8, call this 10, 3 different side lengths. So if a triangle is scalene, then I know for sure that it has no equal sides. That's what it means. That's all you got to know. Equilateral triangles. Let's talk about what that is real quick. So instead of having no equal sides, all sides are equal. Ooh, that's very different. So in an equilateral triangle, we know that all 3 sides are the same length. How could I tell the reader, hey, this is an equilateral triangle? Well, I could put tick marks. That indicates that all 3 are the same size. I could just put a number on there if I wanted, right? If I had like 7, 7, and 7, that would tell me that they're all the same size. So scalene triangles, could they ever be equilateral? The answer is no, right? You can't have no equal sides and have all equal sides. Those don't go together. All right, so we know what scalene means. We know what equilateral means. Let's talk about isosceles. And we're going to be talking about inclusive definitions, just so you know. What does that mean? Well, back when you were just a little kid, at some point you learned what a square was. And you learned what a rectangle was. And you were first taught that these were distinct and different shapes. That is called exclusive definitions. But later on, as you learn more and more, you're like, okay, well, actually, all the properties of a square, all the properties of a rectangle are also in a square. And you're like, okay, well, a square is actually a type of rectangle. That's an inclusive definition, meaning that the rectangle definition includes squares. The exclusive definition says they're distinct and different and that they're not the same. And they both have their purpose. When you're first learning shapes, it makes a lot of sense to use exclusive definitions. You want to know what they are distinctly and not where they all kind of bleed together some. So in math, though, the only thing that makes sense at the highest level are called inclusive definitions. And what is that for isosceles? It is at least 2 sides are equal. At least 2. That's the important part. Not exactly 2, at least 2. So if I have an isosceles triangle, I didn't mean to do that. If I have an isosceles triangle here, how would you know it's isosceles? Well, I could put 2 tick marks, so I know those 2 sides are equal. And that makes it isosceles. Are at least 2 of the sides congruent? Yes. But real quick, is this also considered isosceles? Is that at least 2 congruent sides? Yes. So sometimes, always, or never, can isosceles triangles be equilateral? That answer is sometimes. Isosceles triangles are sometimes equilateral. How about the other way around? Equilateral triangles are isosceles. What do you think? Is an equilateral triangle isosceles? That is always true. Equilateral triangles are always isosceles. They always have at least 2 equal sides. The key word there being at least. So an equilateral triangle is a type of isosceles triangle. Now, if you know it's equilateral, should you call it isosceles? No. Just like here, if you know it's a square, should you call it a rectangle? No. You give it the most specific name that you can. All right, so we have this shape. 2 sides are equal. We need to know some names. We're going to have a lot of word problems, and you can't do the word problems if you don't know the vocabulary. On an isosceles triangle, you have at least two equal sides. Those sides are called the legs of the shape. So we have two legs. The third side is called the base. Real quick sidebar, there's another triangle that has legs as well. It's called a right triangle. On a right triangle, you have two legs. Now, on a right triangle, do the two legs have to be equal? No, they could be like 3 and 4. So the word leg does not always mean equal in general. But when we're talking about an isosceles triangle, the legs must be equal. So yes, legs must be equal on isosceles triangles. We also have some angles here. These two angles are called the base angles. They're the two angles that touch the base. And then this is a tricky one. This guy at the top, this is called the vertex angle. I don't like that name. I wish it was called something else, but it's not. It's called the vertex angle. Not to be confused with a vertex angle. Every corner of a triangle is a vertex, but only one is called the vertex angle. So if I say, hey, angle A is the vertex angle, what do we know about that? Well, the vertex angle is the angle where the two legs meet. So I know that the two sides that touch the vertex angle are going to be equal. I know that the side across from it is going to be the base. I know that the other two angles are the base angles and they're going to be equal. I know a lot of stuff if I know where the vertex angle is. So like if I give you a triangle, something like this, let's call it A, B, C, and I say that angle, let's say angle A is the vertex angle. So if angle A is the vertex angle, and I told you like, what if I said this was 10? Well, then this side has to be 10. Mr. Man, it's not 10. It is 10. If this is the vertex angle, then these two sides have to be the legs. What is one of my goals with pictures this year? My goal is to mess you up. So you can't always trust the picture. If the problem tells you that it's the vertex angle, you just have to trust. The picture will not always be drawn appropriately. If you want to redraw it to make it look better, you can. All right. So let's go look at some things here real quick. I'm going to go over to my friend GeoGebra, and let's talk about some triangles. Right now, I have three. Let me make it a little bit more distinct here. Something like this. Right now, it's a scalene triangle. How do I know that? Well, 10.04, 13.81, 12.19. That's how long those sides are. Those are all different. But what else do you notice? All three angles are different. What else do you notice? I just told you. All three sides are different. Look at the angles. The angles are also different. So for a scalene triangle, you can actually tell that it's scalene if you know the angles. If all three angles are different sizes, then all three sides will have to be different sizes. This is only true for triangles, guys. Triangles are the master shape. They are how we know so much. The actual formula of a circle is the Pythagorean theorem. And I talked about this more in class, but triangles are like the master shape, right? High levels of math are based on triangles. When you play video games, they draw polygons. The equations are triangle based. And the more triangles you can draw, the better the picture or the image looks. So like if you go in here, oh no, where did it go? Oh, it's way over here. So like I have this pulled up. Like if you look at an old video game, a Nintendo 64 could only draw around 125,000 polygons every second. Well, look how blocky it looks. You can see all the corners and the edges. Like look at the nose, look at the hand. They couldn't draw as many triangles, so it didn't look as smooth. Look at a newer video game. Look at a PS5 game. They can draw like 20 million polygons per second. That's a lot more. And I might be wrong with those numbers, but I think I'm right. That's a lot more. And if you can draw 20 million, you can make them look very lifelike and very smooth, but they're still triangle based. Triangles make the world go round. So if we're looking at this, all three sides are different. Now this is really cool. Check this out. Angle A. If angle A were to get smaller, make a prediction here. If angle A gets smaller, what has to happen? So it's kind of hard to lock it in, but I'm going to try to keep this around 13.81. But as angle A gets smaller and the other two sides stay the same, angle A is getting smaller and smaller. What's happening? If angle A is smaller and smaller and smaller, what has to happen to compensate? And the other two sides are pretty close. I was trying not to change them. But this third side, BC, had to get smaller to compensate. Angle A is responsible for the side across from it. The smaller angle A is, the smaller the opposite side is going to be. Right now, the biggest angle is this 94-degree angle. The biggest angle is responsible for the biggest side. The wider the angle, the wider the opposite side. The smaller the angle, the smaller the opposite side. So what would happen if I try to get this to the point where two of the sides are the same? And I'm not going to be able to do it perfectly, but I can sure get it close. Maybe. Something like that. That's as close as I can get it. But look, I have 9.54 and I have 9.56. Let's pretend that they're exactly the same. Look at these angles. 53.87 and 54. Like, if my sides were exactly the same, I promise you those angles would be exactly the same. Well, what angle is responsible for this side? It's the angle across from it. It's this angle. This 54-degree angle is the one responsible for this one. It's this angle that's basically 54 that's responsible for this one. If the two sides are the same, the two angles responsible will be the same. So then what's true if all the sides are the same? Well, let's go look here real quick. So if none of the sides are equal, side note, no angles are equal. That means, like in this picture, all the angles are different sizes. Maybe it's like 50 and 60 and 70. I don't know. Just making some numbers up. If this is the biggest angle, then this is the biggest side, by the way. So did I put them in good corners? No. Do I care? No. But because someone will complain, I'll change it. This really should be the biggest angle just based on how long the sides are, right? So like none of the angles are going to be equal. So if all you know are the angles, you can tell that it's scalene still. How about equilateral? If every side is the same, what do you think is true about the angles? They're going to all be the same. Now, I cannot stress this enough. These properties only work on triangles. It's why triangles are the master shape. We know every single thing about every conceivable triangle, guys. But if I have like a four-sided shape, can I have four sides that are not the same? Like on a rectangle, aren't all the angles the same? But does that mean all the sides are the same? No. Can I have all the sides be equal and it not be a square? Yeah, that's called a rhombus. So this doesn't work on other shapes, guys. I could have different angles on a pentagon or a hexagon and still have congruent sides. These rules only apply to triangles. It's why we're learning about triangles first. It's why triangles are best. So if all the sides are the same on a triangle, that means all the angles are the same. If two of the sides are the same on a triangle, that means two of the angles are the same. And we talked about being responsible, like this side over here, this is the angle responsible. So let's just do a quick example down here. Let's go. If I have triangle ABC and I know that these two sides are equal, okay? What angles are responsible for those two sides? In other words, which angles, like if they got wider, would make those sides bigger? Well, the side CB, this side down here, what angle is responsible for side CB? And it is angle A. If angle A got bigger, CB would have to get longer. So I know angle A is responsible for CB. What's responsible for the other one, AC? What is responsible for this side over here? It would have to be angle B. Angle B is responsible for side AC. So if you know that AC and BC are equal, then you know that angle A and angle B are equal. So in this picture, where's the base? Where's the vertex angle? Where are all these things? Well, this is my base. These are my two legs. This is my vertex angle. And these are my base angles, A and B. So does the base have to be at the bottom? No. The base has to be opposite the vertex angle. The base angles have to be opposite the legs. The base angles are responsible for the two equal sides. All right. Can't spend much more time on that right this second. Let's go look at some other things. Acute, we're going to go through this real quick. What does it mean to be an acute triangle? All angles less than what? 90 degrees. All angles. All three angles. So can I draw an acute triangle? Yep. How would I know that it's an acute? I'd have to get some numbers in there. 50, 60, 70. That's an acute triangle. So every angle is less than 90. How about a right triangle? One angle is exactly 90 degrees. Messed up. There we go. One angle is exactly 90. Now, what would we know if I call this A and B? What is A plus B? It's going to be 90 degrees. So can those angles be right angles or obtuse angles? No. Those angles have to be acute. As a matter of fact, every triangle has two acute angles. Every single one. Every single one, guys. Now, we'll run into this a little bit more, but when I say has two acute angles, I mean has at least two. In math, the way you read math, if they say, like, if this shape has two equal sides, it means at least two. If I say a shape has three equal sides, it means at least three. If I mean exactly, I will say the word exactly. At least is pretty much always implied, because if I said, hey, I got the shape that has two acute angles, am I saying the third one's not acute? No, I'm just saying that the two I know are acute. So it's still possible I have three, so we need to read it as being at least two. Every triangle has at least two acute angles. So I know that those two angles would have to be acute. They can't be 90. They can't be more than 90 because they have to add up to 90. How about an obtuse triangle? It has one angle more than 90 degrees. Oh, wow. So if I draw an obtuse triangle, one of the corners is bigger than 90. That didn't quite do it. I bet I can get it this time. Nailed it. So like maybe it's like 100 degrees. Well, on this one, what is A plus B? On this one, A plus B would equal 40. But that all depends on this one, right? It's just they have to add up to the remainder. Oh, sorry, they don't add up to 40. Who said 40? They add up to 80 because a triangle has to be 180. So I don't know how big A and B are individually, but I know they have to add up to 80. Could they be 60 and 20? Sure. Could they be 40 and 40? Yeah. But I know they have to add up to 80 in this case. If this was not 100, if this was like, 150, now they got to add up to 30. But they're going to be acute, guys. Every triangle has two acute angles. We name a triangle by its third angle, the third choice. Now, if they're all three acute, then yeah, you got yourself an acute triangle. All right, and then an equal angular, all angles are equal. It's kind of in the name. We don't use this one as much, but I just want to throw it out there. If all the angles are equal, how big do they have to be? They have to all be 60. How long is each side? They're all the same size. Equiangular always goes with equilateral. All right, I feel like you guys understand these words, so I'm going to move on. Sometimes, always, never. Right triangles are scalene. So I'm going to draw a right triangle. Can I make it scalene? So that's the first thing, is can it be scalene? And the answer is yes. What would be an example of it being scalene? It could be 60 and 30. There's a right scalene triangle. Now remember, when you read this, right triangle is the premise. Right triangle has to happen. It's the conclusion. Does it have to be a scalene triangle? Well, what is another option? Could these both be 45? Yep. So that's a right isosceles triangle. So this one sometimes. It could be scalene. It could be isosceles. Remember, if all three angles are different, all three sides are going to be different. Well, if two angles are the same, that means two sides are going to be the same. Equilateral triangles are obtuse. So I know it has to be an equilateral triangle. Has to be that. So how big is every corner? If it's equilateral, if they're all the same, they're going to all be 60. Well, can that ever be obtuse? No. So all I have is a counterexample. That's going to be never. Equilateral triangles are going to be acute every time. Scalene triangles are obtuse. So I've got to have a scalene triangle. That has to happen. So can I draw a scalene triangle that is obtuse? Can it be like 100, 20, and 60? Would that be acceptable? Sure. That's scalene. That's obtuse. But could it be scalene and acute or scalene and right? Sure. Could it be like 50, 60, and 70? That's scalene, and that's acute. If every angle is different, then we know every side is different. So you can be a right triangle. You can be scalene can be any kind of triangle, really, except for equilateral, I guess. Obviously, those are different. Okay. Isosceles triangles are acute, so it's got to be isosceles. So can I have two equal sides and be acute? Yeah. Could it be like 70, 70? That'd be 140. Could it be like that? Would that be isosceles and acute? Sure would. Could it be isosceles and something else, though? Does it have to be acute? Well, what about a right triangle? Could it be, we just did that earlier, right? Couldn't it be 45? That's isosceles, but that's a right triangle. So that's another sometimes. Acute triangles are equilateral. Can you be equilateral and acute? Yeah, if all the corners are 60 degrees, then you are acute and equilateral. Well, can you be acute but not equilateral? Yeah, we've drawn a few of these, but could it be 50, 60, and 70? Yeah, so that's another sometimes. Acute does not guarantee equilateral. And then every triangle has two acute angles. That's not a very good question for sometimes, always, never. Actually, it should have said something like triangles have two acute angles. And remember, that is at least two. If it meant exactly two, it would have said exactly two. And exactly two is sometimes. All right, let's talk about congruency then. Congruent shapes, congruency statements. I'm going to go through this kind of quick. Congruent shapes, let's talk about what that means. That means same shape, and it means same size. So if I'm looking at the shape, what determines the shape? Angles determine the shape. So the angles have to be a match. What determines the size? Well, that's the side lengths. So angles determine shape, right? Like if something is an equilateral triangle, it doesn't matter if it's the size of your pinky or the size of the sun. If it's equilateral, it's going to look the same. It's going to be the same looking shape. All right, writing congruency statements. So if I'm looking at this, like this 32, it is included. The word included means like it's in between. It's included for angles I and H. Well, I and H are a 1 dash and a 4 dash. Let's go over here. Here's my 1 dash. Here's my 4 dash. Is that one also 32? It matters where they are. So not only do all the sides have to have a match, but they have to be in the same order. Look at the 13. The 13 is between a 4 and a 3. So if we go over to the 13, is it between a 4 and a 3? Yes. How about the other 26 and the other 26? Yes. So we go around and we make sure that each side is included for the same two angles. And they are. So yes, these two shapes are congruent. They have equal angles. They have equal sides. They have the same configuration. So we're going to name them. It does not matter what order I put these in, as long as once I hit, like if I say J is my first letter, I have to either go clockwise or counterclockwise. No crissy-crossy. Crissy-crossy makes an X. Don't do it. So let's say I go J, K, H, I is congruent. So a congruency statement is king. You have to understand what a congruency statement is and what it's talking about. Like, the order is everything. So what corresponds to J? J has a 2 dash. It's going to correspond to V. I know they don't look like they're in the same place. Don't say it goes with you. The pictures are there to mess you up. The name is based on the corresponding parts. Angle J and V are the same. They're the same angle. They're the same position. Remember, like corresponding, when we had lines like this, corresponding means they're in the same position. They hold the same spot. This is the 2 dash. This is the 2 dash. Those are the corresponding parts. So J goes with V. K, well, K is my 3 dash. So what does K go with? It goes with W. And then H, that's my 4 dash, that goes with T. And then I, that's my 1 dash that goes with U. Now I could have done the first one in lots of different orders. Like I could have said H, K, J, I. If I said H, K, J, I, now I got to say T, W, V, U. So I have some freedom how I start out, but once I have this side, the other side is locked down. The corresponding parts have to be in the same places. And now, so just so you know, like more often than not, I will actually give you the congruency statement. So like what if this was what I told you? I said HKJI is congruent to TWVU. What would you know? Like you would know that angle H is congruent to angle T. You would know that JI is congruent to VU. Those are the things you would know. If I gave you this statement, I don't care what the picture looks like. I don't care if they look congruent. If I give you this statement, you have to trust the statement. Okay, let's do this one. It says, write the statement. What does NMO correspond to? Well, NMO, the same angles on the other triangle would be V, W, X. So those are the corresponding pieces. So what do we know? Like I know here that that ON is congruent to XV. Those are going to be the same size. Look at the picture. ON. Look at XV. They're the same size. Those are the corresponding parts. So the corresponding parts have to be congruent. Angle M. What would angle M go with? Angle M, according to the statement, has to go with angle W. So this is a congruency statement, and it leads you to individual parts being congruent. And that's actually real important here. This is called CPCTC. Don't you dare say that slow. CP. I'm already asleep. It's CPCTC. Let's get it out there. Let's not waste time. But what does it stand for? It stands for corresponding parts, right? It's the corresponding parts or the corresponding pieces of congruent triangles. So the triangles have to be congruent. Corresponding parts of congruent triangles, what do they have to be? They are congruent. Well, duh. Yeah, okay. But it's important to note, if you have congruent triangles, then all of their parts are congruent. That's what this means. That's what it stands for. You're going to be doing some proofs later on. So like if I tell you that triangle ABC is congruent to triangle DEF. Let's say that's part of your given. What are some things you know? Like, could you say that CA is congruent to FD? Yes, we know that from the statement. But if you're writing a proof, how do you tell the reader how you knew that? Well, that's where this comes in. That's where you write CPCTC. The corresponding parts, right? Aren't those corresponding parts of congruent triangles? Congruent triangles, aren't those congruent triangles? Have to be congruent. The corresponding parts of congruent triangles are congruent. That's how you knew it. That's what you write in your proof, right? If you said angle A is congruent to angle D, how do you know it? CPCTC. And you're going to be putting those in proofs. All right, I'm going to do these last two questions real fast in triangle ABC. So I'm going to draw triangle ABC over here. Oh. Okay, I'm doing something wrong. There we go. Okay. It's called triangle ABC, and it says that B is the vertex angle. Oh, if it's called the vertex angle, I prefer to put that at the top. So I'm going to do like this. The vertex angle. If that's the vertex angle, I know those two sides are equal. I know these two angles are equal. That's something you have to remember. The vertex angle. If angle A is 45 degrees, well, angle C is going to be 45. Which means angle B is going to be 90. So name it by its sides. Well, if it has the vertex angle mentioned, it's going to be isosceles. Angles, well, it's 45, 45, 90. That's going to be a right triangle. Right? If it has a 90-degree angle, it's going to be a right triangle. I am not going to solve this whole thing, but I am going to show you the setup. If it's called DEF and GHI, guys, I don't even need the picture a lot of the times. But I do want you to draw it out. It helps you see things. All right. So if I call this DEF, I went top, right, left. D, E, F. Top, right, left. Please don't mess yourself up with pictures. If that's D, E, F, then I need this to be top, right, left. GHI. GH, 5x plus 7. Well, that means this is 5x plus 7. Because what do we know about GH and DE? They're the same. HI, 2x plus 14. 2x plus 14. And DF, 25 minus x and 25 minus x. Now, do those have to add up to 180? Nope. The perimeter is 186. So basically, we know that that has to add up to 186. But it might have been hard to tell if you didn't draw them out and label the pieces. We know that 5x plus 7 plus 2x plus 14 plus 25 minus x equals 186. So 6x plus 46 equals 186. 6x equals 180. So x would equal 70 divided by 3. Sorry. I said 180. I meant to say 140. So 70 divided by 3. That's x. Plug it in, you get it. All right. But that's 100% based off the name. Hopefully you learned something. Hopefully that was helpful. Have a good one.